Sorry about that. So just be careful. Okay. Now, for those of you who are scoring 70s, 80s, you are day here away from being an A. Okay. What did I say in the beginning of class? Oh, I said a lot of stuff, right? What did I say though? I said 1/3 of a class getting what? A's, right? 1/3. How many of us here? About 70? Somebody give me a number. 1/3 is what? Come on, base calculus. 20 something, right? 20 something. How many 90s I got so far? 16, right? I'm a number guy, see? Bad at numbers, but how many more I can have? Around 6 or 7 students, right? How many 80s and 70s I got? Good around 10 students, right? So for 70, 80, and 10 students, right? You might jump into the A category, okay? You might jump into the A category. Okay, now for those of you who score 60s, 60s and 70s, right? I think it's about time we start doing some soul searching, trying to figure out the way we study, okay? Maybe my pace is too fast for you, okay? Maybe you need to do a little bit more work, practice, homework, follow the quizzes, right? Especially the quizzes, okay? If you have any questions, I'm always in my office or sitting in my home, waiting for you to zoom in and we can talk, all right? So I would say that those of you who got 60s, the majority of you messed up the last problem number 4, okay? And I will talk about it a little bit more, okay? Few of you, 1 or 2, messed up problem number 3, which is a doubly reinforced sections, okay? So that's my observations, all right? Okay, any questions about it? Yes?
When is the homework and the quizzes going to be put in so we know our grade?
Yeah, exactly. So I'm working on that. I'm sorry. I just tried to squeeze in, get all this done last night. But quizzes can take a little bit more time because I need to have 7 quizzes. That's 70 multiplied by 7. That's 490 quizzes I have to grade. So it takes about a few days, say this weekend. And homework, I'm actually done. I just need to upload the grade to it. And some of the PDF actually printed out. I need to take a look at what I did. So I say that good timing would be this Friday or this weekend, should everything, okay? But like I said, I wouldn't worry too much about homework and quizzes. You guys are doing a fantastic job there. And I just use that as an interaction tool for me to understand where we're at, okay? But good question. Anything else? Anything else? All right, if nothing else about the exam, all right, we'll talk about a little bit more in the latter half of the lecture today, but here are my exams. I cannot give them to you for free, but you're welcome to stop by after lecture if you want to see your mistakes and all that, okay? If too many of you want to see that, make an appointment with me and we can go over them together sometime, okay? Not bad, like I said, not bad. If you're not happy with your grade, most likely something you missed, but we can take a look at them together, okay? All right, good deal. Okay, so that's about the exam number 1, okay, kind of recap. I want to finish this irregular section, okay, irregular section today. And let me see what's going on, why this is not powering up. Okay, so what's powering up? A quick recap. What we have learned from irregular section. It's irregular compressive zone. It has openings anywhere, right? But what did we really learn from irregular sections? What is the difference between the irregular section and rectangular section? What is the difference? Because the width for the rectangular section is usually given or known. Is that right? Is that right? And for the irregular section, it's not that easy. So 2 things. First, you need to find out how much of compressive area you need to balance the tensile forces from the rebar, right? So that's one thing you need to do. And the second thing you need to do, matter of fact, is that, let me just adjust a little bit. You need to actually find the centroid of the compressive zone, centroid of compressive zone. That's the 2 criteria, right? Just like the T-beam, similarity with the T-beam. In T-beam, we need to find out whether the compressed zone is within the flange or not. In the irregular section, right? Most likely we're going to have openings. We need to find out whether the compressive zone compose or cover the opening or not. That's what matters, right? So that is the only difference. So last time we have talked about the section like this, right? And it was actually a design problem. I threw you a curveball at the beginning, right? So we say that we have a rectangular section, but we have an opening in the middle, all right? And we went in, calculated, and find out that my compressive zone A happened to be magically covering the opening, right? And then from that point, we say, since it's covering the opening, everything's simple. We do a big block minus small block, right? And how to do that is you assume that these blocks follow the Whitney stress block, right? So this thing here has a uniformly distributed compressive stress of 0.85 F prime C and has a depth of A. And this opening here, assume is negative 0.85 F prime C and have a whatever width the opening is, right? So you use that and subtract the opening, got your total moment. Got your total moment. And then you still need to check the strain in the steel. And I have this question from the T-beam from the student, right? In the T-beam, we have the wings on the side, we have the web in the middle. But to check phi, strength reduction factor, right? Is the A only related to the web, or the A is also dependent on the wing? Or let me rephrase. To check phi, right? What do we need to determine phi, strength reduction factor? Think about it. What do we need to determine phi? Epsilon, S or T? T, right? So to get epsilon T, what do we need? Depth, of course, dt. And what else? C, right? To get C, what do we need? A, is that right? A. But in the T-beam, do I really need to worry about A in the flanges? Don't care, right? It is only in the web that I calculate my A. So same thing for the irregular section. You only need to care about A for this irregular section, then find C, find epsilon T to determine the strength reduction factor phi. Okay, so that is the thing only matters. Okay, so with that, we come to this problem here, and I have a irregular section just like so, right? And let me open my notes here. Sorry. And it kind of follow a weird shape that I have some small pieces here, and I have a gap here, and I have opening in the middle, right? So for that weird shape, what do I need to know is, let's see, where is my notes at? Is where is the center of my compressive zone? Where is the center of my compressive zone, right? And to find the center of compressive zone, of course, first I need to calculate the effective compressive area AC to find out whether my compressive zone cover this opening or not, And in last time, I made a mistake. I forgot to tell you what exactly is this tiny reinforcement area is. Right? I just made something here and I said 70.6 at the end of it. So in this problem, it is actually an analysis problem. It's not a design, okay? So for this problem here, AS is actually given, all right? So let me put down here so you know. So AS reinforcement somewhere at the bottom here is given, and that is 4 inch squared, 4 number 9 bars. Yes, okay? And then concrete is F prime C 4 KSI, and steel is 60 KSI, of course. Right? Then we assume everything yielded first, right? Got a total tensile force and let it equal to the compression force and find out AC, and that is 70.6 inch squared. And knowing that's the total compressive zone, we start to check whether this compressive zone covering the opening or not. What we did last time, we draw a line and we say, look, if it covers the opening, barely cover the opening, and assume that is 72 inches, and this is too big, then the 70.6 inch square of calculated required area of AC, then it says that it does not cover the opening. It does not cover the opening, right? If it does not cover the opening, the problem I have at hand is that my neutral axis is somewhere here. And mind you that, folks, this is my tiny opening there, right? The neutral axis just draw across that opening. And the problem is, I don't even know where this neutral axis is here. And let me just call it Y bar. You see a lot of Y bar, right? I just love Y bars, right? I don't know. So how to determine this fellow here? How to determine this fellow here? So the great war artist, Sun Tzu from China said, if you have a lot of enemies, you do what? Divide and conquer, right? You divide and conquer, right? How do we divide? How do we divide? So in this tiny problem here now, if I divide this piece into these two tiny little wings, and I call it area 1. Okay, I call it area 1. Let me just clean up the shaded piece to see better, okay? And now I can also cut the other area, which is this belly area right here, right? And I call it area number 2. And then whatever left is the bottom corner here is I call it area number 3. So the name of the game is actually to find the height of area number 3 here, area number 3 here. So how do I do that? So here's how we're gonna do it. So A1, the total area of this tiny block here equal to a 4-inch. And this final fellow here is 2-inch. So 4 multiplied by 2 multiplied by 2 pieces, right? So got a total of 32-inch squared. Then A2 equal to this belly fellow here, and I have 12-inch in the middle. And the height of this guy here is 2 inches. And apparently my drawing is in the proportional, but 12 multiplied by 2 gave me 24 inches squared. All right. Then I left with A3, but I know that the total compressive zone has to equal to AC anyway. So AC minus A1 minus A2 gives me A3, and AC is 70.6 inch squared. Yes. Is it? Oh yeah, sorry. Did I do that again? So Y and okay. You're right, but I made a mistake here actually. Thank you. You're right, yeah, but dimension is wrong. Okay, it's 4-inch on the side. Okay, thank you. So 70.6 inch squared minus 32 minus 24. Yeah, what I got, folks? What I got, folks? Can I get a check? I have some number, but I'm not sure of a number, right? Help me out here, folks. What you got? 14.6 inch, right? 14.6 inch squared. Great. All right. So I know my tiny area of area 3 has 14.6 inch squared. Okay. So with that, I take a look at it, right? So I say, let me draw it out basically of this tiny area here. And I have these 2 tiny wings. I call it area 3. And now this fellow here, I need to know the distance here. And the distance here is given, which is opening of 4 inches, right? So here's 4. So 12 minus 4. So this is 4 again. This is 4 again, right? So all I need to find out is this tiny height. We call it H3, right? So H3 is area 3 divided by the width of it, which is B, and that is 12 inch minus 4 inch. And then I have a 14.6 inch squared minus an 8 inch. And then I got my H3 equal to a 1.825 inch. So you see this number, 1.285 inch. It barely covered the opening, but it is not opening. Okay, not opening. So I got my geometry, right? I got my H3. So at this point, what do I do? What do I do? What is the mission of this whole operation? What are we trying to achieve here, fellows? Why do we care about H3? Somebody? I just heard something.
Y bar.
Y bar, right? That's Bob's favorite, right? Y bar, right? Y bar, right? And now I got my Y bar promised is this fellow here, which is 4 inch plus 2. So 4 plus 2 plus H3. So eventually I got 4 plus 2 plus 1.825, and I have 7.825 inch. So this is y bar, right? But what exactly is this y bar? Matter of fact, when I draw this an A neutral axis, is this actually accurate? Can I say this is neutral axis or not? So it is not neutral axis. Why is that? Because this y bar here, ladies and gentlemen, is the effective compressive zone size A. Okay, that is not C, which is the actual. This is effective. Okay, this is effective. So in this case, A is y bar is this fellow here, 7.825 inch. All right. Now, what does it mean? It means that for this weird section, for this weird castle-like section, my effective compressive zone is somewhere here, A equal to a 7.825 inch. And that is my total compressive area, AC, equal to a 70.6 inch squared. And that's what it means. Very simple. All right. Okay. So now, some of you may say, Bob, this is a little bit too specific for this problem, right? What if I have a problem like this? All right. Right. And this happened in the exam, right? What you're feeling, right? You're feeling pretty happy? Not much, right? Not much, right? What if I have an exam that I had to do a section like this? Ooh, spicy, eh? That's pretty good, right? What if, have you seen the Squid Game? Netflix, right? What if I have a horrible umbrella shape, right? Oh boy, in the nightmare, and you know what? Cut an opening. You're gonna figure that one out, hey? Right? Right? What if in the Pharaoh, in Egypt, right? There's a nice pyramid, right? And there's a water duct going like this. Oh, symbolic stuff, right? Pretty powerful stuff, right? And now what you're gonna do? Now you cannot do the dumb way Bob did, right? Bob said, oh, draw a line, make sure the compressive zone cover the opening, right? It doesn't work sometimes. It doesn't work sometimes. So in a complicated situation, this approach does not work. So how we can make it work? This is how. So the official solution, right? A universal, powerful tool, it's a O wing-wing scenario is that you do this. Y bar or A, Y bar essentially equal to what? Sigma AI, YI divided by sigma AI. Remember? Just like how we did the bars, right? Find the centroid of it. So this is essentially what it is, right? And now this fellow here, actually, well, anyway, so yeah, I shouldn't do this, but anyway. The center, let me do this. The center of the whole shape here, let me use a different number. X here is this fellow here. And at the same time, sigma AI, meaning all these area add up has to equal to AC. Okay, so this is more of a general approach. So what we have done up here is just trying to find AC and find AI, which is to find this line. And the next step is to find the center of this shaded area. Okay, so how do I find the center of the shaded area? Let me magnify this shape. Okay, let me magnify this shape so you see better. Okay, so now I look at this shaded area, right? And I say now, look, I have a H type of section here. And I have 1 here, 2 here, 3 here. Okay. To find my X, I need to pick a reference. And in this setup, my X is right here. Starting from this distance right here, right? So let's do X equal to A1. And to be consistent and not confused, use xi, so x1. Now, what is the distance between the centroid of 1 to the reference line here? Now, given that this is how much? 4 inch. What is the distance? X1 equal to what? 2 inches. Is that right? Right in the center of it. And 2, naturally, this is simple. And again, my drawing is horrible. 2 inch, right? So this is 1 inch distance away. And with that, so X2 is 4 plus 1 equal to 5 inch. So this is X2. Move this away here, so it'll be easier. Oops. Okay, so this is X2, and that's the center there. And now X3 equal to what? X3 equal to this fellow here, so 4 inch plus this fellow here, 2 inch, and plus H3 divided by 2. All right, and H3 is this fellow here. Okay, so now we have X equal to A1 X1 plus A2 X2 plus A3 X3 divided by the whole thing area, A1 plus A2 plus A3, and you know this value is AC. Okay, so let's plug all the number in. So now I know X equal to A1. What is A1? Now 32 inch squared is A1. We calculated before, right? Here, 32 inches squared. Okay, and 32 inch squared multiplied X1. X1 is 2 inches. Plus A2, which is 24 inch squared, and multiplied by X2, that is 4 plus 2 divided by 2, because you know I have the center of it, so this is 5 inch, and plus 14.6 inch squared, and multiply 4 inch plus 2 plus 1.825 divided by 2, and now divide the whole thing by a 70.6 inch squared, and now I got my X value equal to what? A 4.94 inch. 4.94 inch. All right. So that, fellows, 4.94, where I am. So this is 4.94. So somewhere here. Okay, there's different colors. So somewhere here is my centroid. Somewhere here is the centroid of the compressor zone. Okay. All right. So at this point, I'm very happy. Why is that? Because I have find my compressive zone and find the centroid of compressive zone. Why do I care about the centroid of compressive zone? Why do I care about that? Why do I care about centroid of compressive zone? Because in the next step, you need to find what? M, N. It's a different color. M, N, the moment. And the moment equal to what? ASFY, the tension force, multiplied by distance, right? And the distance would be ds minus what? ds minus what? Half A. Option number 1, half A. Option number 2, I don't know. Option number 3, hurry up, Bob, write it. Which one? Is that right? Is that right? That is the mission of the game, is to find the centroid of the whole compressive zone X. All right? Okay, so now with that, I can continue. Now, AS is 4, number 9. So 4 inch squared multiplied by 60 KSI. And now DS, what is DS? Did I tell you or not? I probably didn't tell you, did I? Yeah, I'm lousy. Sorry about that. Okay, forgot about it. The distance between the top fiber to the reinforcement, and that is given, fellows, for this problem, is 18 inch, okay? To make life easier for you, 18 inch is given, okay? It's not a design. So here, 18 minus a 4.94 inch, and I got my total moment. And again, please check me, okay? How much you got? How much you got? Anybody? Anyone? Anyone? Can I get a number on this? 30. Well, that's in pounds, inches, right? Can I get a conversion to kip foot? So divide everything by a 12. 261.2 kip foot. That's what I got. Anybody get different? I could be wrong. Remind you, right? I'm very bad at numbers, actually, right? I get a different number? No? Okay, good. So that is my moment capacity for this irregular shape. Are we done? Are we done? Can we leave it like this and go home? Can we do that? Probably not. What's missing, folks? Come on, what's missing? Phi, right? What is phi? Call it out. What is it? Strength reduction factor. Now, what is the strength reduction factor dependent on? Is a function of what? Epsilon t. Exactly. So how do I get epsilon t, folks? I use dt minus what? C or A here? C. Is that right? C. Okay. Divided by C and multiply epsilon cu, and which is what? Oh man, after first exam, what is epsilon cu? 0.003. There you go. All right. So what is dt? Well, let's equal to ds, shall we? To make things easier. What is C here? C equal to what? A divided by what? Beta 1. And for 4 KSI concrete, what is beta 1? 0.85, isn't it? You know the number. And then divided by another C here, which is A divided by 0.85. And now multiply 0.003. And know that A equal to Y bar, what I got for A before. What did I have for A? 7.825 inch. 7.825 inch. So please help me out here. What is my epsilon t? Bring this number in. Come on, pull your calculator out quickly. Bring this number in, what do I get? You're pretty good at phones, right? Must be good at a calculator as well, right? Come on, let's do it. Waiting for a number, okay? I have a bad number. I'm waiting for a number. Something? Come again? Okay, 0.028. All right, you see this number. What do you feel? You feel happy? Excited? Sad? Neutral? Don't care? 0.028. First impression, does it yield? Is it bigger than the yield strength of the bar? Yes, right? What is yield strength of the bar? 0.00207. So it yields. If it yields, we're happy, isn't it? At least it yield, right? And now this is referring to the exam. If it yields, is it under reinforced or over reinforced? Under reinforced. So when the yield doesn't have to be more than 0.05 tension control, it is called under reinforced. Okay, that's the regret in their life for those 598. Okay, almost all of them 598. Okay, be careful. Now it yields. Should I be happy though? I am not that happy. Why is that? Because my phi is no longer an ideal number, which is 0.9. Instead, I have to use that equation 0.65 plus a 0.0028 multiply 250 divided by 3. All right, 250 divided by 3. Now what I got, folks? Come on, let's hear it. What I have? 0. 0. What? Yes. Yeah. So sorry. You're right. 0.0028 minus 0.002. Thank you. Yeah. So what do I have? I got 0.716. 716. Exactly. 72. Okay. Round it 2 digits after that. Okay. Now with that, I say now finally, my VMN equal to 0.72. My strange fellow 261.2 kfoot, and that gives me 188.06 kfoot of bending moment. And my friend, that is a sacrifice you make when you have irregular section. You cannot control the feet. You cannot guarantee the always tension control. All right, you cannot. You have to compromise, and that it is the internal battle between us, structural engineer, and those of you guys, architects. You know, like beautiful, elegant buildings. Gotta make compromise here. Okay, gotta make compromise here. All right. If you go on YouTube, you search conversation between the architect and structural engineer, you find a nice conversation there, okay? Instead of debate, a lot of times how both teams work together, okay? Make the structure come true, all right? All right, so here, we gotten done with my irregular section. So why I'm so drilling on this boring topic for you is because in exam number 2, first problem, okay? Even sometimes the first problem, I will give you the regular session. So let me give you a taste, right? And this is what happened in the past, right? I was dizzy-headed first semester here, Mr. S&T, right? Thinking you guys can do everything, right? So that is year 2017 spring. Okay. Right, just like the Squid Games, right? Let's see how my thoughts evolve, right? Then year number 2, right? Well, actually the same year, like next semester, I did this. Okay, I did a tower head. You would put the opening on the top, right? I put opening right here. Yeah. Right? Feeling right. This is 2017 fall. Okay. Then I get even better, right? I get more imaginative. In 2018, I started doing something like this. And guess where the opening is at? Right here. Okay. And then in 2019, all of a sudden, I become a normal person. I say, Bob, you're too hard on the folks, right? I become a normal person that did this. Okay. And all of a sudden, last semester, my heart aches, right? I so wanted to test you guys. I said, look, let's do this. And make it cantilever. Then Dr. Sneed went out of her window, right? She said, no. She said, look, that's too much. And we did this eventually. Okay. So let's see what happened this semester, right? Okay, let's see what happened this semester, okay? All right, I may get creative, right? Think about the Squid Game umbrella, right? When I see that scene, my heart pumps. Oh my God, I finally find a problem for my students. I love it. All right, joking aside, okay? It will be an rectangular section or T-beam or I-beam with opening in it, okay? So forget about this. That was my first semester of a learning curve. It's gonna be something like this, okay? And joking aside, again, it's gonna be either this or this, okay? So practice now, okay? Don't make the same mistake, all right? Okay, that is how much I want to talk about with irregular section, okay? Any other questions, folks? Anything jumps out of paper? We will most likely not going to ask you to design for it. We will most likely just ask you to do analysis for it and won't be doubly reinforced, just single reinforced. Why? Irregular section is so important, okay? It is because on job site, you oftentimes dealing with complex geometries. So it's not always perfect. At least we have openings, put the pipes in for the HVAC and anchoring system, and you might have to fill it back with some silica filling materials, but those things do happen, okay? All right, so that's it. All right, I think I'm gonna end the slides and end the lecture today. Are we happy? No, yeah, I was just joking, okay? Oh my God, see that anxious moment? I'm gonna go now. Not yet, okay? Give me 5 more minutes, please, okay? So let's quickly review the exam, shall we? Shall we? Okay, all right, so I want to open up exam here. All right, I don't want you to record that, but inevitably you probably can do that. So I just hope you won't leak the problem too much, but I'm gonna change the problem anyway, okay? So let me just open it up, I can talk about it. Where is it? Teaching. What did I share? Let me see how I'm gonna share this. For exam number 1. Okay, this is that. All right, open it up. Okay, is it coming out? Okay, this is coming out. Good deal. Okay, so let me share the screen with you guys. Can you guys see it? This is your midterm, okay? Midterm, okay? All right. Oh, not seeing. Okay, sorry. Let me just drag it over here. Again, I have some problems sometimes. Still not too big. Come on. Come on. Oh boy, I hate it. Okay, this is good. All right, not again. All right, so I think you guys see it. The first problem, consider the beam with cross-section shown below. The beam is positioned bending this way, and that's the diagram. And the effective depth D is what? Let's hear it. What? What do you choose? Which one? Which one? Which one? I got a 16.15, get 2.5, got 14.75, and 17. Which one? 16.15, right? 16.15. Okay. So how do I get that? How do I get that? You get a Y bar, isn't it? You got a Y bar, right? Some of you just didn't do the Y bar and assumed it's for number 9, for number 8, and went from there, you did a mistake. Okay. So that's the first one, 16.15. Okay. Second one, truth be told, at the last minute, I throw away the other 3 versions, only keep this version. So all of you are testing on one version, okay? Apologize. I just want to say my grading work a little bit. And it works, okay? I didn't see anybody cheating, so I'm pretty happy about the outcome. But next year I'm gonna change, okay? All right. Strength, I have A, B, C, D, and throw out A, C, and D, only left the B version, that's okay. The strength reduction factor phi, all right? Now, how do we determine phi? Among all these strengths, which one we're going to pick? Which one we're going to use to calculate phi? The 0.0046, isn't it? So what is tension control? What is tension control? 0.005. So you look at them, which one is closest to 0.9? Which one's closest to 0.9? D, right? So I picked that, 10 seconds. Okay, you calculate, you do the same thing, you got the same number. There you go. We got a lucky winner there, right? Cannot bet on luck all the time, but sometimes you can, right? Here, number 3, the cracking moment RC section. How do you do that? FRI, right? FRI divided by H or height, right? Middle of section, right? And that is 10 inches, right? And what number you got? What number you got? What number you have? Folks, come on. 40.3, okay? 40.3. Oh, yeah, I got some weird number. Somebody even write some number out here. So, Bob, none of them are right. My heart sunk, right? Number C. Okay. Now, reinforced concrete beam, problem number 1 is what? First of all, does it yield? Has it yielded or not? Yes, right? Yielded. Oh my God, right? You did well. I don't know what's going on now today, right? Yielded, okay? Yielded. So yielded, under reinforced, over reinforced. Under reinforced. I got one guy, very good student, went into A and B, very fine. But now A or B? A or B? Is it transition? Is it tension control? Is it tension control? No, right? It has to be B, right? Game of elimination, right? Only a lucky guy stayed the end, right? Only the lucky one stayed the end, right? So number B, transition, no, okay? This problem 1C for the reinforced beam in the problem 1A. Oh, I don't want this. I don't want to print. If it is cut, oh yeah, you're so smart, yeah. Cut in place, exposed to weather, which one have? 1.5 or 2? We had a battle, some lady in that section shout out 1.5. Every time I say 2, 2, 2, 2. So guess what? 2, right? It's probably 2. Check in the table, right? Check in the table, it's 2, okay? I just love 2. Tell your fellow friends, your fraternity, sorority friends, Bob like 2-inch cover. Next semester, I'm gonna change it back to 1.5, right? That's how the game plays, okay? But you guys, check the table, 2 inches right here, okay? I'm gonna run quickly. I got it for a few more minutes, I think. Which of the following statements is true? Stress strain relation for steel is the same as stress strain compression, basically symmetric, asymmetric, yield strength reinforced steel tension lower, and A and C, which one? Which one? Is steel symmetric or asymmetric? Symmetric, right? Meaning stress strain curve is the same in tension and compression, right? So A, okay? Which of the following statements is true? Steel building generally faster, steel faster time than occupied than reinforced concrete building. Reinforced concrete building generally have a faster time. Steel building, concrete building generally have the same time. In the cast place, reinforced concrete architecture finished cladding cannot be installed until after the entire structure is completed. basically saying A, steel is better, B, concrete is better, C, the same thing, D, I don't know what I'm talking about. Which one? Which one? Concrete is always better. I still got a few guys feel like they're in the steel lectures, right? You go to steel, take the exam there, steel is better than concrete, yes. Right? You go to concrete, concrete is better than steel, yes. Right? Oh, come on, man, right? And why is that though? Because concrete what? Concrete what is more of sectional, right? It doesn't need to weight anything, right? It can go stage by stage, right? Remember that it takes shorter time to occupy because you can do the cladding, everything while you're doing the elevation. Steel is different, you gotta wait, right? You gotta wait, okay? You're joking, so I need to know that, okay? Now this is number game. Beta 1, 0.825. Is this one slower, lower than 8.5 or higher than 8.5? Sorry, 0.85. Higher or lower? Lower, right? Meaning the strength is higher than 4 KSI or lower than 4 KSI. Higher, right? So A is out, okay? And 0.25, did we say every 1 KSI is an increment of what? 0.05, right? So this increment of 0.025, so means it has to be a 500 in it, right? So which of the three have 500 in it? 45, right? So here, I bet again, I bet right, right? You didn't bet, you did the calculation, messed up, you make wrong, right? Didn't understand the problem deeply, okay? All right, so number 2, this is B, number 2, okay? The yield strength on the concrete 40, grade 40 reinforcing bar is what? Grade 60 is what? What is yield strength for grade 60? Come on, 0.0207. Grade 40 is lower or higher than that? Lower or higher than that? Lower, right? So the strength is lower or higher? Lower, right? So no calculation needed, A, okay? This one here, number B, you know that, right? Just read out, right? It's just textbook. 1I, this is my favorite part. And I put 5 pointers, right? I'm so worried about your method multiple choice. I give you a freebie. No, but yes, guess what? I have so many people didn't even get this freebie, okay? So which one? Same area as actual concrete compressive stress distribution and nominal flexural strength. Yes, it has the same centroid. That's why we can use it, right? So A and C. I probably didn't emphasize this enough, but I thought you know, okay? And truth to be told, I only have 3 students messed up, so I'm not so disappointed, okay? So 3 of you should know what's going on here, okay? 3 of you should know what's going on here, okay? So this problem, quickly, just bear with me for a second, okay? Here, B mean 12.17 inch, okay? 12.16717, okay? B mean 10 inches, okay? If you got 9 from table E5, I'm sorry, folks, no point, okay? I said specifically do the calculation, right? Effective depth, that is 20.6, 20.6, 20.59, 20.61, 20.69 even, I gave you points, okay? I give you credits. How do I do that? I need to find my white bar, okay? Mind you, I have 2 number 6, 3 number 7. The white bar is not exactly in the middle, okay? You got to calculate for it. You got to calculate for it, okay? So now this problem. So that's 15 points. Oh my God, right? How easy I made it for you guys. That's all right, just joking. Anyway, most of you guys are fine, by the way, okay? This problem, first of all, is it negative or positive bending moment? Negative, right? So which one is the tension bar? 3 number 9 or 2 number 7? 3 number 9. Here, if you guess this, I saw this for your scratch paper, 5 points. No question asked. Very good, very happy, right? Then how to find this? Do the iteration. C is, what's your final C? After iteration, what's your final C? What is final C? About 4 inch, right? Some of you got a little bit this wrong on that. Go back and check, okay? Or come to see me around 4 inches, okay? And then 3B, minimum reinforcement. What is the minimum reinforcement? Equation 3 square root of prime C BWD divided by Fy, or 200 divided by Fy multiply BWD. I got 2 students forgot to multiply BWD. I got some weird numbers. Standard answer for this, 0.91 inch, 0.97 inch. Which one's bigger? 0.97 inch square is bigger. So that is a minimum reinforcement area. Do I have enough? Yes, you sure do. 3 bigger than 0.97. Duh, right? Good. How about this one? String diagram, no need to say. Just draw it, right? Not hard. Now this, oh my God, right? I've seen all kind of weird answer trying to find the moment. For a cantilever moment, what is the equation for it? We went through this. For the distributed is what? 1/2 omega L squared. Is that right? Omega being the distributed load. What is for live load? PL multiplied by 6 feet. That's it. I have seen omega L squared divided by 8. I have seen omega L squared divided by 385. I don't even know where the number coming from, okay, folks? So be careful, right? Then the final number around 19 or 20 kips. Anywhere you got close, I gave you credits, okay? 19 to 20 kips, okay? Go back and do this. And one thing before, don't forget about the phi strength reduction factor when you do this, okay? Don't forget about that. Now, final problem, right? Oh, my beloved continuous span beam. What a glorious problem, right? Section A, section B, which one is positive, which one is negative? A is what? Negative, right? So before you do anything, you put the bars here on the top, I give you 5 points, flat out, no question asked, right? And still I got a one guy flipped. Okay, I don't know what happened there. Okay, so here, if the beam is restricted 14 inches, right? And you do the calculation, blah, 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 you end up with 400 something, right? And close to 300 something, barely cover the 380, you're fine, right? The depth's about 20 inches. DS is about 20 inches, 19 or 20 inches, right? Add everything up, your height should range from 18 to 25. Your height, total height, okay, ranges from 18 to 25. Anything like there is fine. Now, the biggest problem I have is about the reinforcement. To design, either 5, number 9 bars, or 4, number 10 bars, right? So you can fit 4 number 10 bars in. Can you fit, let me say this for last question, okay, very important. Can you fit 5 number 9 bars in this beam? Depends. If it's one row, no, you cannot, sir, man, you cannot. All right. I see people didn't do calculation, jam 5 darts in it. Please try it yourself. Didn't work. There is a way, and there's 1 or 2 smart guys actually, ladies actually did that. 3 bars at the bottom, 2 bars on the top, right? So yes, you can fit number 9 bars, 5 of them. But the problem is when doing that, you have to recheck your D, right? You have to recheck your D. Some of you forgot to do that. Okay, but in general, if I see 4 number 10 bars and spacing the right, 30 points. Okay. All right, thanks. That's it. Appreciate it. And if you have questions, come back here, we can talk. Okay. Question? Yeah.
I just want to look at James Shealy. Yeah.
Privacy. You can take a look and ask me questions, but don't take your exam away. Okay. I haven't finished everything yet. All right.
Good to see you.